So, if you're watching the frontier of computing right now, especially in, these really volatile fields like machine learning, there are two financial realities that are just forcing this fundamental architectural change.
Right.
Fact one is that Moore's law, that predictable doubling of transistors we all relied on, it's definitely slowing down.
No question.
In fact, two, the cost of designing custom silicon, I mean, these specialized chips, ASICs, it's just staggering. We're talking about needing maybe $500 million.
A half a billion just to develop a single cutting edge 5 nanometer chip. That cost structure means for most companies, ASICs are becoming, well, economically out of the question for anything but a massive fixed market.
Which is exactly why FPGAs, these field programmable gate arrays, they aren't just an alternative anymore.
No, they're the strategic imperative for customizable hardware.
We always come back to that great analogy the source uses. If the ASIC is that perfect, specialized bronze sculpture, designed for one thing forever.
Yeah, the FPGA is like a collection of infinitely reconfigurable Lego bricks.
Exactly. The power is in that ability to adapt, sometimes overnight, without ever going back to the fab.
But those Lego bricks, they've always had a penalty. For decades, the Achilles heel of the FPGA was just the sheer amount of area and power consumed by its programmable interconnect.
All the wires and switches that stitch the logic together.
Right. And of that penalty, historically, it came from the multiplexer transistors that sat at every switch point. They were what delayed the signal.
And what we're diving into today is why that fundamental trade-off has, completely inverted. Because at the advanced technology nodes we're using now, 7 nanometers, and below the transistors are fine.
The transistors scaled perfectly. They're efficient.
Our problem is physical. It's an architectural crisis caused by the wires connecting them.
That's it exactly. So our mission today is to really get a quick grasp on this wall of physics that has just shattered decades of human design intuition. We're going to reveal how automation and these new hybrid architectures are really the only path forward for saving reconfigurable computing.
Okay, let's unpack this. And I think the best place to start is with the foundation. How did we even get to the dominant FPGA design that we use today?
Well, you have to trace the DNA back to the early 1980s. The modern FPGA, it really evolved from these early kind of awkward solutions like mask-programmed gate arrays.
Which needed that final, costly factory step. Yeah.
Exactly. The true revolution was the Xilinx XC2064. It introduced two concepts that are still at the core of every device today. First, prefabricated wires. The routing is already fixed on the chip. And second, stored select multiplexers controlled by configuration SRAM cells.
And for most of FPGA history, the entire industry kind of converged on what we call the island-style architecture.
Yeah.
So you have these islands of programmable logic blocks or CLBs, and they're surrounded by channels of routing wires. Why did that specific pattern win out for so long?
Because of regularity. It provided this uniform structure that just solved a lot of scaling problems. It made it so much simpler to integrate large, specialized blocks like hardened digital signal processors, or DSPs, without messing up the whole structure.
I see.
And crucially, its grid structure also meant that designers could easily adapt all the powerful placement and routing algorithms that had been perfected for the ASIC world. It created a predictable performance environment.
So we had decades of these stable design principles until effectively we tried to go below 10 nanometers. And this is where the wall of physics hits. We hear this term a lot, but what is the core physical mechanism that completely broke that island-style model?
It really just comes down to basic electrical physics and geometry.
Yeah.
As we scale the transistors down, we have to scale the connecting wires down too. We shrink their cross-sectional area.
Okay.
The problem is that electrical resistance doesn't scale linearly. It actually increases quadratically as the cross-sectional area shrinks. And when you get down to the thickness of 7 nanometer wires, you start seeing these other physical effects like increased electron scattering, and that causes resistance to just surge dramatically.
That's the crucial mechanical difference then. The logic gate itself is getting faster and smaller.
But the wire connecting it to the next gate is fighting back.
Yeah.
Precisely. Interconnect delay, which was once, a secondary concern, it now completely dominates the intrinsic delay of the transistors. The sources give a truly stunning detail on this. The electrical resistance of a typical 7 mm-like local wire can be more than 4 times higher than its 16 mm counterpart.
4 times higher. For what seems like a small reduction in size, that's not a scaling problem, that's an electrical collapse.
It is.
And this collapse, it leads directly to architectural inversions that just defy everything designers assumed was true.
Oh, absolutely. And the most shocking one involves the relationship between local and global connectivity. For decades, the mantra was always keep signals local, keep them fast.
Because we assumed the shortest paths were the fastest paths. It just makes sense.
Of course, but those short local connections, the ones routing signals within a tightly packed logic cluster, they rely on the finest pitch, most resistive lower metal layers.
Ah, so that's the trap.
That's the trap. Those lower metal layers are now so resistant that the local interconnect is often slower than the global interconnect. Global paths, by contrast, they use the much thicker, lower resistance upper metal layers to travel between clusters.
This is the part that is so counterintuitive, it just sticks with you.
Yeah.
The delay to cross a large cluster locally, let's say routing between lookup tables or LUTs inside one block,
hmm
that can now take longer than the delay to just route globally to the cluster next door.
The visual example is startling. The time it takes to get from the bottom LUT to the top LUT in the same cluster can actually be longer than getting to the bottom LUT in the cluster above it.
Your shortest physical path is no longer your fastest electrical path.
Exactly.
And this completely shattered the old rules for optimal logic grouping, too. For years, the perfect cluster size was what, 8 to 10 LETs?
That was the sweet spot, yeah. But now, if just traversing the internal wires inside that cluster carries a massive delay penalty, that big cluster becomes an electrical liability.
So the physics is actually pushing us towards smaller, effective cluster sizes.
It is, because that local routing cost has just become too high. And we see vendors reacting to this. Intel's Agilex architecture, for example, has broken down its local interconnect into smaller lanes, specifically to shorten those extremely high resistance wires.
And AMD Xilinx did something with Versal, right? The supercluster.
Yeah, with the supercluster concept, they basically created a secondary network just to offload the high volume of non-critical feedback signals. The goal is to preserve a fast global path for only the absolutely critical timing signals that determine the chip's clock speed.
These are brilliant engineering fixes.
They are, but they are localized tactical responses.
Right, because what the vendors are really doing is trying to design their way out of a combinatorial optimization problem that the human mind just it cannot grasp in full. They're solving symptoms, not the underlying complexity explosion.
That's the strategic issue. The only path forward is mandated automation. We've really reached the end of intuition. FPGA pioneer Stephen Trimberger once said that back when Moore's Law gave you a guaranteed 4 to 5% gain every month, you could afford to rely on instinct. He said, nothing clears up decision-making like realizing you do not need any of the data.
You just moved fast.
You just move fast.
Yeah.
That era is completely over. The reliance on instinct is now impossible because the number of architectural variables has just become too vast.
So human intuition will just consistently miss the optimal solution now.
It's not even a question. The complexity is literally astronomical. When you're designing the programmable interconnect, the exact switch patterns, it is a massive combinatorial search. For a relatively simple switch block, the number of possible permutations can reach approximately 10 to the 57th power.
10 to the 57. I mean, just to ground that number, that's more than the estimated number of atoms in our entire galaxy. A human cannot map that space.
Not a chance. Automation is necessary not just for speed, but because it's the only way to systematically search for these non-obvious optima.
It doesn't get distracted by the old rules of thumb.
Exactly. It searches for the new rules that are dictated by 7-nanometer physics. And this required a whole new automated design paradigm that really relies on 4 key pillars.
Okay, let's run through those 4 pillars that define modern FPGA design.
So first, you have automated switch pattern design. Automation systematically searches that massive design space to find patterns that minimize 2 things: multiplexer area and, more critically today, the capacitive load that those multiplexers place on the now highly resistive wires.
Okay, and second is regularity-constrained exploration.
Yeah.
So the automation can't just find a theoretically perfect solution, it has to be manufacturable.
Correct. The final architecture has to fit the factory floor. So for example, the tool must be constrained to ensure all multiplexers of a certain type are exactly the same size. This balance between physical practicality and mathematical optimization is essential.
Right. And the third pillar is automated fixed connectivity design. We can't let every single signal travel through the slow, programmable fabric.
This is where the hybrid nature really starts. Automation identifies specific, non-programmable express lanes or direct connections that are most beneficial for bypassing slow multiplexers for signals on the critical timing path.
And the fourth pillar. This feels like the most fundamental shift of all. The mandate for co-design with placement algorithms.
The hardware and the software, they have to be developed together in an optimization loop. A beautifully designed architectural feature, like a new express lane, is completely useless if the CAD software can't find it and can't exploit it.
So the algorithms have to be developed right alongside the hardware.
They have to be, so the placement tools can optimally arrange the logic right next to those high-speed paths.
This brings us squarely to the modern reality, the hybrid future. We're not really designing purely programmable chips anymore. We're designing these sophisticated systems built from a mix of flexible and fixed paths.
And you have to start with the cost of that flexibility. Programmability costs you, and it costs you dearly in both area and performance. The main area constraint is the configuration SRAM cells.
These are the tiny transistors that hold the bit stream, right? The instructions that define what each gate does.
Exactly. They are the stored blueprint for the chip's behavior. But their scaling has slowed down so much compared to the logic transistors. The sources report that even back at 20 nanometers, these SRAM cells took up an astonishing 50% of the total routing area.
50%? Wow.
And because they scale so slowly, the area overhead of flexibility is only getting worse. It demands that the fixed paths carry a huge part of the load.
Okay, so let's look at those fixed paths because they come in two really different types now, each with a specific job. First, the most granular option. Direct LUT to LUT connections.
These are the express lanes, implemented right inside the logic cluster. They bypass the general routing fabric completely, offering ultra-low latency and very predictable performance for critical paths.
And when they're co-designed with the CAD tools, they get real results, right?
Tangible results. Studies show they provide a post-routing delay improvement of about 4.3%.
And what's extraordinary is the efficiency. The area overhead is tiny. You can add an optimized pattern with just, 1.13% of the logic cluster area? That's a huge return on investment for speed.
It really is. It just highlights the sophistication of the automated design process. Then, at the complete opposite end of the spectrum, you have the hardened networks on chip, or NOCs.
And these are not for local critical timing signals. They're for moving big chunks of data, right?
Precisely. They handle high bandwidth, long-haul communication using standard packet-switched routing. They're designed to connect the programmable fabric to major dedicated blocks, like high-speed memory controllers and AI engines.
And the big payoff here is area savings.
An immense advantage. Building that communication network out of specialized hardened logic rather than general programmable logic, well, a hardened no-C router can be up to 22 times smaller than its soft logic equivalent.
So the modern FPGA is this beautifully orchestrated division of labor. The no-C handles the big data streams. The direct connections handle the critical latency-sensitive paths.
And the general programmable fabric handles all the arbitrary, flexible logic that is specific to the user's application. It's a synthesis born from engineering necessity. We're no longer forcing every signal onto one expensive, slow, general-purpose fabric.
We're using the right interconnect for the job.
Exactly.
And finally, we can't really talk about fighting the wire resistance problem without acknowledging that optimizing the 2D surface is just step one. The ultimate long-term tool for fighting wire delay is, it's moving upward into 3D integration.
Absolutely. We've already adopted what we call 2.5D integration, where you use a silicon interposer to connect multiple smaller chiplets. This lets architects create enormous FPGAs that would be just impossible to manufacture as a single high-yield die.
It also enables that heterogeneity we just discussed, right? Combining components from different process technologies.
For sure. You can have a 7mm FPGA fabric dice connected to specialized high-bandwidth memory dice, or HBM, all in one package. But the real promise for fighting the wire resistance problem, that lies in true 3D stacking, where one die sits directly on top of another.
And the idea there is to move the area-hungry components.
Specifically those configuration SRAM cells. If we can move them onto a separate die that's stacked vertically, the logic die itself becomes significantly more compact.
And that compaction is the key.
Yes, because compaction inherently reduces the average wire length for connections within the fabric. And since length is a core factor in resistance and delay, stacking the SRAM directly attacks the primary source of signal latency in these modern technologies.
So if we step back, what does this whole architectural crisis really mean for you, the listener? I mean, the era of relying on predictable scaling and accumulated design intuition is completely over. The physics has broken the old rules, and the complexity of the solution has just grown beyond human capacity.
The future of FPGA performance relies entirely on the sophistication of the design process itself, not on the intrinsic shrinking of silicon features anymore.
The core takeaway then has to be co-design. That symbiotic optimization loop where the hardware fabric and the specialized architecture where CAD tools have to be developed together.
Hmm.
Because if you build a fixed connection, but your placement algorithm, like a specialized integer linear programming or ILP algorithm, doesn't know how to place the logic to exploit it.
That connection is useless. The hardware potential just remains completely unrealized.
Success today means systematically finding these optimal, non obvious ways to align logic to the hidden high speed paths that automation has discovered, paths we couldn't even map using human intuition.
The complexity of connections, not the size of the gates, is the new frontier.
That is the big shift. The true innovation is no longer in the logic gates themselves, but in the intelligent architecture of the wires we use to talk between them. So here is a final provocative thought for you to explore. What design challenges in your professional field are currently relying on old rules of thumb or decades of intuition that a systematic, data driven, automated search approach might completely shatter? We've reached the end of this deep dive.